Joey?
Yes.
Everyone okay?
Yes. I don't have any formal introduction though, so all rely on you and also Professor Georgia.
Well, anyway, you will chair the whole thing. I will just say a few words.
Yes.
I will say a few words, and Howard will explain, give the best introduction.
Obviously, Steve doesn't need much of an introduction, but I will say a few words.
Yeah, of course.
And Juven, my name is George I.
George I. Great. I'm actually curious the origin of this name, if that can be asked.
The family story is that it's Eastern European from the Hungarian roots, but it's been a long time, and I don't think we want to delve too deeply into our family history. It was apparently a little shady in spots.
Yeah. I guess the speaker is not here yet, no?
I hope he's not having internet problems.
Anyway, Julian, you should let him speak whatever length he wants to, because he is not young. So you should make sure that he is more relaxed.
Yes, sure.
On the other hand, he's not like David Gross, who will talk for 3 hours.
Right.
I think it will be harder and harder to locate Professor Weinberg when the audience number is increasing much faster. No. I think Professor Weinberg is here.
Is he?
Yes.
Okay. So we start.
What I think we should see. I make Professor Weinberg a co-host right now, and then see whether Professor Weinberg is ready.
Is he going to be sharing a screen? You might want to check that that works if he is.
Yes.
Yes, exactly. That's what I'm trying to do. All right. Can you hear me now?
Yeah.
Yes.
All right. I'm going to try to load a file.
Yeah.
This is an unfamiliar thing. I haven't. I think I'm not seeing. I may have to leave and load it and then come back in.
Okay.
Yes. Don't worry. Take your time.
Well, all right. Oh, there. Okay, good. I got out of full screen. That's what did it.
Okay. Are we ready to go?
So Professor Weinberg,
Are you ready?
are you ready? Or do you want to take a bit more time?
Oh, there it is. There it is. Good. I've been teaching by Zoom all year. You'd think I would be more adept at this, but it's all very strange to me. Okay. All right, I'm ready to go, I think.
Okay, great. So, ladies and gentlemen, it's a great honor for CMSA in Harvard to host this meeting, Quantum Matter in Mathematics and Physics, that Professor Steven Weinberg will give this talk. And he is the greatest scientist in high energy physics still alive. And I think it's a great honor for us to have him. But I have the honor to meet him several times, and I really admire him. And now I'd like to ask Howard Georgia to introduce him, who would know him far better than any of us. So Howard.
Thank you. It's always a special day when Steve Weinberg returns to Harvard, even virtually. There are many remarkable things about Steve, but to me, the most amazing is that he has been a crucial contributor to many areas of physics for over 60 years. I can't think of any other physicist who has been so consistently inventive over such a long career. Steve was the Huygens Professor of Physics at Harvard in the great years from 1973 to 1983. I think these were pretty good years for Steve as well, since he shared the Nobel Prize in 1979. In this period, I had the privilege of getting to know him and sometimes collaborating with him. And these experiences affected me deeply because I got to see a bit of Steve's unique way of looking at physics and the world. I am very eager to hear what he's thinking about now. So please.
Thank you, Howard. It's a great pleasure to be back in virtually in Cambridge. A little frightening too, you know, when I see the title of a lecture series and it uses the words Harvard and mathematics, I feel I'm just not up to presenting anything that's mathematically sophisticated. I generally haven't. Well, once in my life, when I was very young, I proved a theorem that used the Heine-Borel theorem. That's the most sophisticated mathematics I've ever used. What I'm going to do today is to, instead of report some recent results, although there is one recent result, I'm going to express a lot of opinions, and I'd be interested to get your reactions on how you feel about these things. The general topic is
Professor Weinberg, excuse me.
Yes.
Your camera is not on you, and also you are not currently sharing the screen, just in case you are.
I'm about to share the screen. Oh, the camera is not on me?
Yes, it's not. Oh, no, it's not on you.
Well, that's because I must be. No, I have the stop video isn't on.
We see the top of your head.
Oh.
A great view of the curtains.
Oh, I see. Oh, okay. It wasn't electronic. It was geometric. That was the problem. All right. Howard, it really is good to see you. You're right next to me on this screen. And thank you for those kind words. I really enjoyed my time at Harvard, and above all with you and Sidney Coleman, I think, were the two who most inspired me.
We miss him terribly.
Oh God, yes. Well, I will now get rid of you all and share a screen. Let's see how I do this. Yes. Well, I'll start with some things everyone knows. Massless particles have been at the center of the development of quantum mechanics since the very beginning. Everyone knows that in 1905, Einstein assumed that the energy of radiation comes in bundles, each bundle having an energy h bar omega, where omega is the circular frequency of the radiation. In 1922, by studying the scattering of X-rays by electrons and observing the increase in the wavelength and hence the decrease in the wave number of the X-rays, Compton was able to show that these X-rays carry a momentum. Well, these bundles carry a momentum h bar k, where k is the wave number. Since omega is absolute k times c, the energy is absolute p times c, which is just the relation between energy and momentum you expect for a particle of mass 0. However, that doesn't get you very far. These particles soon became known as photons, named by a chemist, actually. But just saying that the energy and momentum come in bundles doesn't tell you, for example, how to calculate the interaction of these bundles with matter. The historic approach to photons was to adopt a known time-honored field theory, the Maxwell theory, and quantize it. To quantize it, you need an action or a Lagrangian. This classically is the action that gives you the Maxwell equations. And this, and as you see, and this is a peculiarity of quantum mechanics, you can't describe the interaction of charged matter with electromagnetic fields without introducing potentials. The scalar potential phi and the vector potential A had already been introduced, in fact, by Maxwell. Maxwell wrote his equations in terms of them, but soon in classical electrodynamics, these were regarded as mere mathematical conveniences. The real physics was in E and B. But in quantum mechanics, you can't get by with just E and B. You have to write the action in terms of a vector potential and a scalar potential, which is what you assume in the purely electromagnetic part of the action. This theory, of course, has to be independent of your particular choice of A and phi, which we say is invariance under gauge transformations. Making a gauge transformations leaves E and B unchanged. And this theory is gauge invariant if rho and J satisfy the conservation law. Now, this classical theory was then quantized by a number of authors, Born, Heisenberg, and Jordan. Actually, what they quantized was a scalar field theory, which they took as a kind of stand-in for an electromagnetic theory. But then the electromagnetic theory was quantized. Dirac, Heisenberg, and Pauli, Fermi. The problem in quantizing it, as everyone who's learned quantum electrodynamics knows, is that there's no canonical conjugate to phi. The variational derivative of the Lagrangian with respect to phi dot is 0. So that certainly doesn't satisfy canonical commutation relations. And what has always been done is to choose a gauge. And if you choose in particular Coulomb gauge, you get for a free field, you get the familiar expansion in terms of the creation and annihilation operators, A and A adjoint, of photons. And you can then use this in a expansion in the interaction to actually calculate whatever you want to calculate. A adjoint of K and plus or minus creates photons with momentum. Is someone saying something? What? Is there a problem?
It was an accident. Please continue.
Okay. Yeah, it doesn't really matter how much of this you hear because everyone knows all this. And one discovers from the quantization of the electromagnetic field that these photons come in two states with helicity, meaning angular momentum in the direction of motion, plus or minus h bar. So we, unlike an ordinary massive particle of spin 1, this is a particle of spin 1 in which the helicity 0 state is absent. Now, this is generalized to cases where the gauge transformations involve matrices, originally done by Yang and Mills in 1954, and that became the basis of the standard model developed from 67 to 73. 1973, the application of these ideas to the strong interactions by Gross and Wilczek and Politzer. Now, it's important that in doing calculations where you may have a self-energy calculation for the photon, gauge invariance protects the masslessness of the photons and the gluons, and would protect the masslessness of the W and Z if it was unbroken. It would also protect the masslessness of the quarks and leptons. And indeed, all of the particles of the Standard Model are, in a sense, massless, except for spontaneous symmetry breaking. The one exception being the Higgs boson, which whose mass is not protected by any symmetry, and therefore somewhat mysterious. Now, the same can be applied to the gravitational field with a lot of hand waving, and the conclusion there is that gravitons come, which are the quanta of the gravitational field, come in two states like photons, but with velocity plus or minus 2 h bar instead of plus or minus h bar. Now that is the standard view of photons and gravitons and massless bosons in general. But there's another point of view, which I think is grounded in work of Wigner in 1939, who starts with the particles. And then you learn about fields after you thoroughly understood the particles. And you can do that just using the tools of group theory. One particle states are always representations of the little group, which consists of Lorentz transformations that leave the momentum invariant. I'm now taking h bar equal 1. And well, everyone knows this notation. The summation convention is in force. And therefore, the unitary operators representing this subgroup, the little group of the full Lorentz group, are act on one particle states, not changing their momentum, but producing a matrix transformation of what other index sigma, which initially you don't know anything about, goes along with the momentum. And these matrices are representations of the little group in the usual sense. Now, this is all very simple, and in fact, a little more sophisticated than you really need for massive particles. In that case, you can take the standard momentum, which defines the little group. Oh, by the way, of course, once you work out the way that particles transform under the little group, particles of standard momentum k, then it's trivial to work out how they transform under arbitrary Lorentz transformations, which of course change the momentum. But the study of the representations of the little group are really all you need to do in order to identify the properties of these particles. Now, as I was saying, for mass not equal 0, you can take the standard momentum to be 0. The little group, which is the subgroup of Lorentz transformations that leaves k equals 0 invariant, is just the rotation group, SO3. Everyone knows its representations. That's what you learn in non-relativistic quantum mechanics. So there's really no problem at all. For mass equals 0, there is a problem, which Wigner pointed out. And that is that, well, here you can't take the standard momentum to be 0. You could take it to be the momentum, an arbitrary momentum massless particle going up the z-axis. The Lorentz group includes, of course, rotations around the z-axis, but it also includes some odd transformations that behave like translations. The little group is, in fact, E2, the Euclidean group of the plane. If you take an infinitesimal element of the little group, that is, in general, a completely general infinitesimal element of the little group is the unit matrix plus some other matrix. This other matrix, in order for a W to be a Lorentz transformation, has to be anti-symmetric. And for this to be in the little group, it has to annihilate K. Now, the omegas that have that property are not just omega 1, 2, which are the infinitesimal rotations around the 3-axis, but also omega 1, 3 plus omega 1, 0, and omega 2, 3 plus omega 2, 0. So if you expand U to first order in the omegas, you have 3 generators, J3, T1, and T2. And from the structure of the little group, you can find that J3 rotates the 2 vector, T1, T2, and T1 and T2 commute, just like translations in the 2 plane. Now, if the physical states are eigenstates of T1 and or T2 with any non-zero value, then you also, because you can rotate, you get you have eigenstates of T1 and T2 filling out a circle. All the eigenvalues that are produced by taking that eigenvalue with definite numerical values of T1 and T2 and rotating it around the 3 direction. Well, at this point, you may have to wave your hands, but we certainly don't know of any continuum degree of freedom of massless particles. And Wigner had some argument about the specific heat of the vacuum, which I never understood. But at any rate, I mean, he didn't spell it out. So the conclusion is, at least to have any resemblance to reality, that the physical particles that we want to consider are representations of the little group in which T1 and T2 are represented by 0. And J3 has some eigenvalue, sigma, which we see as the helicity, because this is the angular momentum around the direction of motion. Now, the question then arises, I haven't said anything about fields. These are just the particles. What kind of fields can create or destroy, let's say destroy, particles like this? A field is characterized as a representation of the homogeneous Lorentz group. And what kind of representations are allowed for a given type characterized by momentum and helicity? Well, really, helicity is the important thing, of massless particle. Well, when I say it can destroy it, I mean that psi has a non-zero matrix element between the one particle state and the vacuum. You know, I think I can give myself a better cursor. Can I? I can't see the cursor that I'm using. No, I'm afraid.
We can see the cursor, and it looks fine.
You can send me a cursor? Oh, do.
We can see the cursor.
Oh, you can? Oh, you're saying you can see it?
I can see.
Yeah, unfortunately, if I can't see it, then it's likely to be at the wrong place. But, well, I'll continue. So I'm asking what kind of field You can see the cursor. Oh, there it is. Yeah, I see. What kind of field defined by a representation of the homogeneous Lorentz group can have a matrix element between the one particle state and the vacuum? Now, obviously, if you apply a little group transformation on here, this, that is to say, if you put in here U of W, U inverse of W, then you know that U of W, you know what U of W, U inverse of W does to psi. You also know that U acting backward on the vacuum gives you 1, and U inverse, well, you can, it's trivial. You know what U acting on the one particle state does. So the two ways of calculating this tell you then that there is, in order for U to be non-zero, this matrix element, you have to have a statement that the little group representation acting on U is the same as the Lorentz group representation acting on U with indices in the appropriate places. Now, since the infinitesimal generators T1 and T2 of the little group have to give you 0, that means that the corresponding infinitesimal elements of the Lorentz group have to give you 0. And that's a powerful condition. The general irreducible representations of, well, the tensor representations are representations with an arbitrary number of antisymmetric index pairs and any number of additional indices. These are space-time indices carried along as a kind of tail. You have to have anti-symmetry between the indices in a pair, symmetry between pairs, and symmetry among. I'm trying to see my cursor, but I can't. And symmetry among the indices that are just carried along. If you want this to be irreducible, that is, to not allow the possibility of factoring out smaller representation. What happened here? Why did that pop up? Are you seeing this weird thing here? Oh, McAfee. God damn them. They pop up all the, how can I get rid of this? Hello, can you hear me?
Yes, we can hear you.
Are you seeing this thing that says Hulu?
No.
No,
We're not, but I am. And it's I can't see my own screen, and I don't know how to get rid of it.
You can just drag it to the side so that it doesn't.
Drag it to the
text.
side. That's a good idea. If I can find my cursor, I can drag it. It just suddenly popped up. All right, I found my cursor. Now, yeah. Oh, well, that's as far as it lets me drag it, but at least it lets me show the, I can see what I'm doing now. If you also want these to be irreducible in the sense that you can't get anything, any other representations by contraction of indices, then contraction of indices between index pairs has to give you 0. Contraction between an index pair and one of the hanging indices has to give you 0. Contraction of two hanging indices has to give you 0. And the epsilon symbol contracted with a pair of index pairs has to give you 0. And this means that the representations are the tensor representations of the Lorentz group that are irreducible are represented by Young tableau, where for each index pair you have a column of height 2 and then a number of columns of height 1. The fact that you're limited to columns of height 2 is, of course, because there's an epsilon symbol. So if you had, for instance, a column of height 3, you could apply, well, then you could apply the epsilon symbol and get a column of type 1. So this is the complete set of irreducible representations of the Lorentz group. Now, which of these can characterize fields that describe a particle of arbitrary helicity? And of course, I'm not limiting myself here to helicity 1. The basic condition is that, as I said, that T1 and T2 annihilate U, and U, then the theorem is that U can be non-zero only for fields with a single index pair, felicity is plus or minus 1. With 2 index pairs, felicity is plus or minus 2. Except you can always have a number of loose hanging indices represented in the Young tableau by these things sticking out to the right, which are, it turns out, are physically irrelevant. In fact, they just represent what you get if you apply derivative operators to these things. For instance, if I took d by dx lambda psi mu nu, I would have a Young tableau with 1 column of height 2 and 1 extra index on the right carrying the index, 1 extra box on the right carrying the index lambda. And of course, that's always possible. And that would also destroy a particle of felicity plus or minus 1. But leaving aside that trivial exception, these are the only fields that can destroy and hence describe particles of felicity plus or minus 2. Furthermore, these fields are all exterior derivatives, that is, curls. Psi, in the sense that the matrix element of psi mu nu is d mu a nu minus d nu a mu, where a is something. And if you, this is a jump now, if you assume that the quantum field has the same structure as the free field, then under you can assume that, but then A cannot destroy a photon in the sense that I described. Or let me put it this way: if A has to be able to destroy. What I said just then was stupid. A has to be able to destroy a photon, a particle of felicity plus or minus 1, which seems to contradict the theorem. But the answer is that A can't be a 4-vector. It has to be a 4-vector only up to transformations that leave this combination d mu a nu minus d nu a mu invariant. And these, of course, are the gauge transformations. Note also that this combination, which is an anti-symmetric tensor with 3 indices and hence equivalent to a vector, this combination also has to have vanishing matrix elements between a 1 photon state and a vacuum, because it doesn't satisfy the theorem that the only possible things are antisymmetric tensors. And if you generalize to quantum mechanics and assume, well, this is zero, you have Maxwell's equations. That is to say, d mu psi mu nu has to be a 4-vector because psi mu nu is a tensor. It's got to be gauge invariant. That is, it doesn't depend on A in any way. And on the other hand, this combination is zero. These are Maxwell's equations. So Maxwell's equations go along as consequences of the existence of massless particles of helicity plus or minus 1. If you try to describe such particles by a field theory, you have to get Maxwell's theory. Well, there's one small exception, and that is you could imagine that this quantity, which is a vector current, is not zero. It would then be the current of magnetic monopoles. And so there is a physical assumption here that there are no magnetic monopoles. Similar remarks can be made about gravity, and I'm just rushing through it. You can't describe a field that destroys and creates photons and is really a tensor, not just a tensor up to gauge transformations, as anything but a tensor with 2 index pairs, and likely Riemann tensor. And then when you run through it, you find that you get Einstein's theory actually what you get is the version of Einstein's theory with the energy momentum tensor with linear equations for H, the departure from unit metric, but with the source including the nonlinear terms in the Einstein field equation. A well-known version of Einstein's theory, also in classical physics. So anyway, to sum up what I've said so far, there are 2 ways of looking at at massless particles. You can start from a field theory that you think you know because of experiments, Maxwell's theory or general relativity, and derive the existence of massless photons and massless gravitons, particles of helicity plus or minus 1 and plus or minus 2. Or you can start with the particles, and with a little bit of hand waving, there are no magnetic monopoles, for instance, you can derive Maxwell's theory and general relativity. And here's a question mark. Which is the right way of looking at it? Well, you can say that this is a bad question, that these are 2 complementary ways of looking at the same thing. And you ought to keep both in your mind, which is not unreasonable. But in a certain perspective, you really have to choose. Many of us theoretical physicists have in mind the idea that there are laws of nature, which we don't yet know, but are final in the sense that everything that is not just an accident can be derived from them. And in the derivations, we'd like to know which bits of our present knowledge are more directly derived from the laws of nature and which are less directly. If A and B are both true, like Maxwell's theory and the existence of massless photons, call them A and B, and the final theory implies A from which we deduce B, or implies B from which we deduce A. Deciding between the two gives us some clue as to the final theory. For instance, in string theory, although I'm not an expert, I believe that we discover the existence of massless photons and Yang-Mills quanta and gravitons as necessary bound states of a string whose existence follows from the underlying symmetries. By underlying symmetries, I mean charge conservation and the SU3 or whatever it is in the Yang-Mills theory, or general covariance in general relativity. No, I would say energy momentum conservation in general relativity. General covariance comes later. So string theory strongly suggests that in this choice, we should think of massless particles this way rather than this way, meaning as more fundamental than the field equations, and try hard to derive the field equations from them. Now, this is all old stuff, and I'm just talking. I don't think I've said anything that you all don't know. Just maybe the question is worth raising, but I haven't said anything new. The one new thing I want to say is that this theorem about what kind of field can describe a massless particle can be extended to higher dimensions. This is something I did last year, and then the work was completed by Jacques Dissler here in our group. And I won't go through the history of who did what, but in space-time dimensionality D, the little group is O of D minus 2. When D is 4, that's O of 2, which is the little group I'm sorry. This is the little group that leaves the that satisfies the condition that the extra generators annihilate the one particle states. The little group is larger. This is not the little group. This is the semi-simple part of the little group. And the particle states are represented by tensors with symmetries given by Young tableaus. There are irreducibility limits on the height of these, but for instance, for D equal 5, you could have height 4. You have anti-symmetry within columns, symmetry between columns of equal length. And by the way, Howard was helpful to me in relearning about Young diagrams while I was doing this. And furthermore, the totally anti-symmetric part of any pair of columns has to vanish. Now, the matrix elements of the kind of field, this is the kind of particle you can have, and satisfying the condition that the the non-semi-simple part of the little group gives you 0. The kind of field you can have that destroys such a particle is simply the same Young tableau with an extra row on top. The extra row increases the height of all the columns, and it gives you extra dangling indices, which just represent derivatives of what you already have. Yeah, that's what I said. If you have a total of n space-time indices, and there are d in the top row, then this is the d derivative of suitably anti-symmetrized. In other words, it's the external derivative of a tensor without the top row. In other words, with n minus d indices. And the same general remarks apply if you want to make a theory of massless particles with dimensionality higher than d = 4, as people have been doing now for just a century. I think Kalutz's first paper was 2021. Excuse me, it was 1921. It's a very old idea, but this is the general statement of what kind of fields can destroy what kind of particles. The particles are not characterized by a number, the helicity, but by a representation of the semi-simple part of the little group, which in 4 dimensions is just a rotation in the plane, and hence the particles are characterized by a helicity. In 5 dimensions, they're characterized by a spin, a representation of O3. And the kind of particles that you can, the kind of fields you can have that represent a given particle are given by this theorem. That's the only new thing I have to say. Now, I've only talked about bosons. I'd like to say a little bit about fermions. This extension to higher derivatives applies to general fermion fields, which transform like the direct product of the fundamental spinor representation in d dimensions and an arbitrary vector representation, tensor, I should say, representation in d dimensions. I won't talk about that except to say that works out in d dimensions very much the same way. The one I want to make a remark about good old spin a half fields in 4 dimensions. These spin a half fields have to transform according to the fundamental representation of the Lorentz group, and the condition that T1 and T2 give you 0 acting on the states actually gives you the mass 0 Dirac equation. So the Dirac equation also for neutrinos, for massless neutrinos, is also something that follows from the nature of the particles. It doesn't have to be assumed as a separate thing. However, there is a question that in this theory, if I extend this to quantum mechanics and say that gamma mu d mu psi is some current J, what keeps the massless particle massless? In the case of bosons, we know that that was gauge invariance, but there's nothing like gauge invariance here in this simple case. I think the answer is they're not massless. In the 1960s, solar neutrinos through the experimental study of Davis based on the astrophysical calculations of Bacall, suggested to Pontecorvo that neutrinos have small masses, something that's been confirmed in numerous terrestrial explanations. So the question is, why do what gives neutrinos their mass? They're not protected by gauge invariance from getting masses, but still, why do they have masses, and why are the masses so small? I think there are two explanations, which in the spirit of impartiality, I call a plausible explanation and an implausible explanation. The plausible explanation is that the renormalizable standard model provides only the leading term in an expansion in powers of energy divided by some fundamental very large mass. And lepton and baryon conservation are just accidental consequences of the fact that in the renormalizable standard model, where we only looked in zeroth order in E over M, there are no terms allowed by other symmetries that would violate lepton and baryon conservation, leaving aside non-perturbative effects, which may be very small. But next to the leading order in 1 over M, there is a term which violates not baryon number, but lepton number, and gives neutrino masses of the order of some dimensionless coupling times the square of the expectation value of the Higgs field divided by this large mass. In an SO10 theory of Howard's, there is indeed such an interaction in the low energy limit of the theory, where M is the mass of one of the large, is a large mass that appears in the SO10 particle multiplets. But these remarks are not dependent on that. It's just in general, from the point of view of effective field theory, it's the most natural thing in the world that there should be lepton number of violating terms suppressed by one factor of 1 over n. Now, if just waving your hands, you guess that G is 0.1, M is 10 to the 15 GeV, suggested by a paper of Howard, Helen Quinn, and me, then you get the result of the neutrino masses of the order, very, very crudely, of 0.01 volts. Experiment doesn't give you the neutrino masses. It gives you the differences in the squares. Since there are 3 masses, there are 2 differences in the squares. And they are respectively experimentally about 0.05 electron volts and 0.009 electron volts. I'm not saying that this is a numerical agreement that verifies the theory, because obviously I've been pretty, presumptuous in assuming these values for G and M. But I will say that this makes it, that the discovery of neutrino masses with these square differences, root mean square differences, makes this assumption very plausible. The implausible explanation is that there is another right-handed neutrino which interacts with the left-handed lepton doublets and the Higgs doublet in just such a way as to produce an ordinary Dirac mass for the neutrino. And I find this thoroughly implausible because it leaves it doesn't conserve lepton number, and it leaves you complete, it's renormalizable. If this exists, you would expect it to be part of the standard model, and it would leave you with the question why the neutrino masses are not comparable to all the other lepton masses. So I think this idea of a Dirac neutrino, in addition to requiring the introduction of a new particle for which there is no other need, doesn't really solve the problem. Whereas the standard with this use of effective field theory really is a plausible explanation of the neutrino masses that are observed. Well, I don't know if I've used up all the time, but thank you very much. Enjoyed talking to y'all. And if you have any questions, I'll be glad to get them.
Thank you very much, Professor Weinberg. Maybe we should all thank Professor Weinberg for the wonderful lecture. Wonder whether maybe Professor Joja, do you want to say a few words, or you want to ask audience to take questions?
Yes, I think clearly Dan Harlow has been trying to ask the question for a while, so why don't we do that?
Sure, so Daniel, go ahead.
Well, yeah, so I wanted to ask about this comment that having a massless photon implies Maxwell's equations. I think you're implicitly taking a low energy limit when you say that, because, for example, there could be a term like f to the fourth in the action or something like Born-Infeld, and then the equations of motion would not be Maxwell's equations.
Pardon me, I know what you mean, and I think that those terms could be lumped into the current. You would still have Maxwell equations, but with a current that involves F mu nu. I don't regard that as different. I mean, that's what you would get, for instance, if you assigned electrons magnetic moments that are different from the Dirac value. You would get just such terms, but they could be regarded as terms in the current, just like the nonlinear part of the Einstein field equations can be regarded as terms not in Einstein's T mu nu, which is a true vector, but in tau mu nu, which is a pseudo, T mu nu is a true tensor, and which satisfies covariant conservation laws. T mu nu colon nu equals 0, semicolon nu equals 0. Tau mu nu satisfies the ordinary conservation law. Partial nu tau mu nu equals 0. I think this doesn't pose any problem for the point of view I'm expressing.
And you would say the same about higher curvature terms in the gravity action, r squared?
Yes, exactly, I would, yeah.
Okay, thanks.
I think Einstein's, but what you said about low energy limit is exactly right. If you are really generous and allow the current with which gravity interacts to contain arbitrarily high powers of the curvature and derivatives of the curvature and so on, then you get the simple Einstein equations as a low energy limit. That's always the way it works, that the simple theory we're familiar with is the low energy limit of an effective field theory. And the structure of the effective field theory is governed by the fact that it has to describe massless particles of a certain representation of the little group.
Thanks.
Next, there's Ariana.
Yes. I have a question concerning T mu nu and tau mu nu, because the status of the energy momentum, or there had been a lot of discussion about that. Now, as far as I know, you were the first who introduced Hilbert's way of defining the energy momentum tensor as derivative with respect to the background metric into quantum field theory. But you didn't make much about it, as if you had gotten it from somewhere else. But I certainly didn't find it in Schwinger's papers or so. Do you remember about that?
Well, I can give a clear answer to that. The answer is no, I don't remember. I haven't thought seriously about these things for many years. If I want to refresh my memory, I go back to a book written in 1972, my first book, and it has all sorts of things in it that I no longer remember, but I'm pleased to be able to look up in there. No, I'm sorry, I can't help you.
Yeah. Okay, thank you.
Arkady Weinstein.
Hello, Steven. Thanks for. I'm trying to ask you in connection with this spin 1/2 massless particle. When you talk about this, lepton number, non-conservation, whatever. What about this chirality, like discrete symmetry, which you also can use, right? About massless particle, but you didn't mention this, so you would not consider this as a relevant to preservation of mass equals 0?
Well, I certainly would in the standard model, where chirality is an accidental symmetry. That is, the standard model is automatically invariant under this discrete chiral transformation, and that protects neutrinos from getting masses within the standard model from radiative corrections, for example. Chirality is not a symmetry of this dimension 5 operator, the one that's proportional to 1/m. And so I would say it's looking backward from the perspective of effective field theory. We should never have taken chirality seriously as a fundamental symmetry.
But leptonic number you also can take it the same way, right? So
yeah, exactly. I would say the same about both.
Yeah, I see. Okay, thank you.
Well, it's 10:30 and I'm talked out, so I will say it's been a pleasure to talk to you and look at some of your faces. Well, Harvard was a great time. I had a great time at Harvard when I was there, and I'm glad to see how active and thriving it still remains. Goodbye, all.
Great to
Yeah,
see
great.
you.
Thank you very much. Thank you very much.
Thank you.
Okay,
Thank
bye.
you. Thank you. Bye.